For the past 10,000 years, agriculture has been a key component of any civilization, and arguably the most important factor leading up to our society today. The Green Revolution of the 20th century kick-started a move towards intensive agriculture. Increased mechanization and intensive applications of synthetic fertilizers has allowed us to produce more food than ever before. But it is this, along with monoculture and poor land management practices, that has caused extensive damage to our ecosystems and biodiversity. This is largely due to injection of excess phosphorus, an integral element in biology and life. Adenosine triphosphate is responsible for providing the energy of most chemical reactions in organisms. Abundant access to phosphorus in the form of phosphates allows crops to return a high yield. Unfortunately, phosphate molecules are also highly soluble and readily enter the hydrosphere. It is here that they do the most damage, fertilizing waterways and promoting the growth of cyanobacteria. These algal blooms can be toxic and block light from entering the water column. Not only that, but the large amount of decaying material that results depletes the water of dissolved oxygen. So the burning question is, how do we continue to practice agriculture in the capacity to feed 7 billion people, while doing so in a sustainable manner that doesn't harm our ecosystems? The manner in which phosphorus is tied to the biology of most living organisms does not make it feasible to distance ourselves from its use. The challenge is grand, especially in Australia, but as we are about to find out, it is not impossible.
Australia has always had a history of low levels of phosphorus in their soils, which is why the need for fertilisers has risen to ensure that crops can receive the amount of nutrients that they require. Due to the latitude and low mean elevation of the continent, Australia has a generally arid climate. Shallow nutrient-deficient soils combined with low average rainfall make Australian agriculture highly dependent on various fertilisers. The problem with this is that over-fertilisation can have highly detrimental effects to the crops it's being used on, and also to the surrounding environment. Surface runoff created by human urbanisation is rapidly creating significant problems in the biogeochemical flow of phosphorus. Development of roads and pavements results in a decrease of nutrients percolating through the soil. Phosphorus is then relocated into rivers and seas, transferred across surfaces which do not allow for the circulation of nutrients. Fluvial transport of topsoil from farmlands into freshwater systems, causing eutrophication, has been a problem in not only Australia, but worldwide. By dramatically increasing the level of dissolved phosphorus within a waterway, nutrients idyllic for algal growth are established. The cyanobacteria which are produced rapidly remove the dissolved oxygen, eventually leading to death of marine animals, known as mass fish death. These areas that succumb to oxygen depletion are termed dead zones. There are multiple dead zones across the world where surface runoff has created these destructive blooms of cyanobacteria. And these bacteria are not readily eaten by fish and zooplankton and thus accumulate rapidly in size. These hypoxic areas cause decreases in fish reproductive activity and the size of the reproductive organs. This can lead to socio-economic instability in regions where humans are heavily dependent on marine life.
The availability of phosphorus and nitrogen is a major barrier in agricultural production and associated high yields. Application of this in agricultural, industrial, and domestic use has heavily disrupted the natural cycle of phosphate in waterways, particularly around urban areas. Unfortunately, fertilizer runoff is the major contributor of nutrient contamination in the Swan River catchment area. Two major challenges must be overcome to control phosphorus loading: reducing input from sources and removal of reduction in highly contaminated areas. As tributary rivers and streams flow in a gravitationally favourable manner, it is difficult to determine the source of phosphate input. In an effort to relieve the pressure phosphorus fertilizers are implicating on Australian waterways, several strategies have been devised. Out of these, the most efficient strategy is the use of an irrigation runoff recycling system. By recycling the topsoil and water that runs off during heavy rainfall, levels of phosphorus entering neighbouring waterways have proven to be greatly reduced. In a drought-affected country such as Australia, systems like this are likely to become quintessential. The next main strategy in use at the moment is limitation of phosphate fertilisers by local governments across Australia. By cutting down the amount of phosphate fertilisers and only using those when actually necessary, it will help to reduce the overall phosphorus levels, eutrophication, and other impacts as a result. Phosphorus is a requirement for any form of agriculture worldwide and must be maintained. With every use of phosphorus, a small percentage isn't returned to the soils. Nauru and Banaba Islands are textbook examples of depleted phosphate reserves. Originally one of the highest quality deposits in the world, by the early 2000s, approximately 80% of Nauru had been strip mined. This has resulted in an environmental catastrophe, causing the endangerment and extinction of indigenous birds. The economy of the country saw an extreme boost from the profits of phosphate mining. The exhaustion of the mining deposits caused an unemployment of 90% of the population.
The mining and removal of phosphorus can be proven detrimental to the environment as over time it leads to ecosystem retrogression. As phosphate does not occur freely in the natural environment, the mining process required to obtain it can leave traces of heavy metal deposits such as lead and uranium. Strict management of phosphate mining byproducts needs to be instated to ensure there is no groundwater leaching. Like other non-renewable resources, there is a finite amount of phosphate rock left available for human use. In a similar fashion to oil production and consumption, phosphate rock production will ultimately reach a maximum rate. This peak is determined using current known phosphate rock reserve levels combined with the rate of rock extraction from the earth and consumption through human use. With only an estimated 75 to 200 years of usable phosphorus remaining in the world, efforts to reduce loss of phosphate need to increase. Approximately 2/3 of the world's population will starve if phosphorus reserves are fully exhausted. Without phosphates, fertilizers will become redundant and crops will not yield the levels required to support the global demand for food. Overall, the challenges of phosphorus management are far from insurmountable. As always, the major barriers are energy and finance. A key concept is that mitigation should not be applied as a blanket solution. The dynamic nature in which phosphorus interacts with the environment based on hydrology, geology, and climate requires solutions to be assessed on a case-to-case basis. As the estimated peak of phosphorus production approaches, growing demand for the mitigation of phosphorus wasted combined with the reclamation of free phosphorus currently existent within wastewater and manure is unprecedented. The use of too much phosphorus leads to possible extinction of marine life, yet overmining of the resource can lead to the crippling destruction of economies such as in Nauru. This planetary boundary needs to be protected, for if it is ever to be crossed, the world will descend into utter chaos and may never return to normal.